Hello everyone, welcome to the DigiTech’24 conference session on the fascinating world of mining and resource extraction. Today we're focusing on mine planning and how information technology can help improve the efficiency and optimization of mining processes and transportation. We would like to invite you to participate in our survey to help us better understand the current state of mine planning and where the industry is headed. Your responses will be invaluable in helping us shape the future of the mining industry. Please scan the QR code to open the survey questions. Let's plan and shape mining together. Your participation is completely voluntary, and your responses will be kept confidential. Thank you.
Okay, good afternoon, ladies and gentlemen. My name is Antony Benham. I'm the director from the MSA Group. It's my pleasure to welcome you to this third session of the DigiTech’24 conference. We have 6 excellent speakers in this session, and I'd like to encourage all participants before we start to use the QR codes that are being hopefully displayed on the screen now in order to participate. Your responses will be used by the organisers to inform the content of future events. So the more people we have who can contribute to these, the better the overall evaluation process will be. So thank you for your participation in this. Without any further ado, and to make sure that we try and keep to the schedule, I'd like to introduce the first of our speakers in this session, Angelov from Kazzinc, Technical Manager for Kazzinc. And Angel will be talking about leveraging Pseudoflow for enhanced underground mine design and scheduling, a case study. Angel, the floor is yours.
Thank you, Anthony. Добрый день, коллеги.
Good day, dear colleagues. My name is Angelov, and I am the mining engineer. I work in Kazzinc. For our Russian-speaking colleagues, I will switch into English language so that it would be easier for me to speak.
Is about a terminology today called Pseudoflow, and I think many of you are probably not familiar with this terminology, and that's what I'm here to do, is to explain to you today what is Pseudoflow. Now, I know that we've just left, we had a good lunch, so everybody is feeling quite lazy, and I'm going to, in this case, create a very provocative presentation. Right. Just to kick off, who is Kazzinc? For many of you that don't know, so Kazzinc is it's a fully integrated zinc business. We produce copper, lead, gold, and silver. We're located, and most of our operations are based in East Kazakhstan region of Rida and Altai. We also have operations in the northern portion of Kazakhstan, in a town called Kokshetau, and close to the center, Zharem, where we have open pits. So this is just a map showing you where we're located and what is our business. So why are we here today? Well, we're here today because we're in the mining industry, and it's an industry with great volatility. Our job is to understand the volatility, but also be able to react to this volatility. If you take a look, this is just some data that I've been able to pull out from the internet that's readily available, but you can see that, for example, the metals that we're mining today, copper, zinc, and even gold, are highly volatile. There are periods of time, over very short periods of time, where we see prices can go up and prices can go down. And so we need to create mine plans that are robust and able to address these changes. How will we do that? We'll get to it. Something that is a bit more important for us locally is the industry that we are operating in today in Kazakhstan. We've recently had some changes to the metal extraction taxes, which has significantly impacted the viability of projects. We also are aware of the strategic move and the recalibration of prices, or even, let's say, the labor costs. So we know that this is happening, and as you can see, some of these figures are quite significant. We're looking at about 20% increases in labor costs over a very short period of time. And the mining industry has to be able to react to these and address it in the strategic plans going forward. Just something else that I picked up is Kazakhstan fuel prices. We know that we're one of the lowest fuel economies in the world, yet we will be starting to see an increase in fuel costs, and these are going to impact our mining operations. So a key question that a mining engineer has to always answer is, where do we mine next? Maybe not so much for coal miners because everything is there and you can see it, but definitely for the base metals and in particular precious metals, we need to know very clearly where we will be going next. A comment made is that the NSR value, or the net smelter return, is an indicator which we cannot rely on solely. Key questions that we get asked is, if you want to invest more capital and you want to develop into new areas, will this maximize our profits? And then the very next one will be, well, what's the mining sequence that you need to have in order to address this kind of volatility and increase in costs, and make sure that you are indeed mining the best areas you can mine. So taking a step back, what is the mining process, or what does this planning process look like? Well, it all starts with geology. So Anthony, you'd appreciate that I did put in a geology slide. And from there, we go into various iterations of optimization. I've just put in here an open pit scenario where we generate nested shells. This is something that many of you would be familiar with. It's the typical Lurch-Grossman optimization of figure out what is the optimal shape of a pit based on the geology and some geotechnical parameters. And then we go into what we call scheduling, or just a mining out of the blocks. So how does this all look when we're talking about underground mining? Well, this is where Pseudoflow comes in. So Pseudoflow is essentially an algorithm, and now I might confuse everybody, but it solves the minimum cut and maximum flow problem. And what it tries to do is it tries to find the best route of extracting value in a certain area. So it's finding the best way to flow through a system. It's a mathematical algorithm, and this was, in fact, initially developed about 60 years ago, if not longer, by Lurch-Grossman, and was eventually optimized and improved as we had more computing power. So the fact that technology is where it is today allows us to improve these kind of mathematical algorithms that enables us to generate quick optimizations, or quick, how would you call it? Quick optimizations, if you would. Just a comparison, so if we look at Pseudoflow and Whittle, the results are absolutely the same, but the speed of processing is significantly faster. So what was our problem? Our problem at Kazzinc was we were using the traditional method to figure out what we should be mining next. We used an NSR cutoff, or a net smelter return, which is based on the value of a suite of metals. And we were using this to determine which stopes, or which areas we would be making money if we were to mine it using the current assumptions, and which areas we wouldn't. However, these processes or systems were Excel-based, so they were quite onerous. It took a lot of time to plug in numbers into Excel, and they were done, stope by stope or block by block, and it took us a long time. We needed something really fast. Why? Because we also had the request from our managers to generate quick iterations with varying assumptions in order to meet the criteria that's given to us. So the Pseudoflow came up as an option for us to look at, and what it does is it essentially creates it looks at an algorithm and says, where would I create the most value if I was to go and mine in a certain way? If it doesn't create value, it would signal that as non-profitable areas based on the current criteria, and it would just give you the areas that are generating a positive discounted cash flow. Now, the one setback here was that there is no discounting. It's an undiscounted optimal valuation. In simple terms, what we see here on the screen is you've got a typical ramp or a decline. So there's central infrastructure that's used to access certain blocks or certain areas. So there is a cost associated with it. And then we have areas or stopes where we generate revenue from. So those are revenue generating activities. And the algorithm picks the highest value after it's considered all the costs it would need to get to the revenue blocks. So the Pseudoflow process is essentially running an iteration through understanding of costs and revenue of all our activities, and the algorithm produces the highest value areas that we can go to, and then we start to use those in order for us to prioritize our sequence. So we might say, well, the current market setup requires us to go very aggressive. We might need to high grade certain blocks of our operations, or we might have to, for example, in the current gold setup, we might be looking back and saying, well, can we go more volume, mine more material? And now we can use this tool to help us prioritize those areas of the operation. The tool's fairly easy to set up. You essentially just need revenue and cost. And you need to know what your costs are going to be. So this is probably the next key question would be, which costs do I want to include in this optimization? And we've, as a company, decided that lump sums, expansionary costs, company overheads, corporate taxes, or even closure costs should probably not feature in this kind of optimization. So we're only looking at the actual costs to mine the ore, and probably some sustaining costs. And this, the Pseudoflow, what we call a Pseudoflow factor, is essentially a cost revenue factor. So if it's below 1, it makes money. If it's above 1, it doesn't make money. If you change your parameters, the factor will always stay the same. If it's below 1, it still makes money. Some of the quick wins that we've had, or just the projects, this is one of our projects where initially, as you can see, given the design and given the stope geometry with the axes that we've designed around it, is a revenue factor greater than 1. It doesn't make money. So this design is inefficient with current parameters. We then go and start to adjust it, whether we design it differently, whether we take out stopes, whether we change the way we access the stope, until eventually we get to a revenue factor less than 1. There, it passes our stage gate, and we can allow it to feature in our mine plan. So just in conclusion, so you've got the traditional methods where you're looking at resource categories and risk rating. You've got revenues per stope, but that is not enough to determine where you mine. Once you start to look at the highest revenue sequence, you start to see that there are areas, even though they might be high grade, that do not make money. Interesting facts that you can see, traditionally we would have had a cutoff that you can see around about here on the blue line, where operating and sustaining capex would exist. All of those stopes on the left of that line would have been not considered in the sequence. However, they are all profitable. So this is just one example of why the traditional method of working out the cutoff is not working. In summary, the Pseudoflow tool is easy, it's quick to use, and it helps both long-term and short-term mining engineers to successfully sequence and design underground metals mines. Thank you. And in acknowledgements, I just want to acknowledge the people that are behind the scenes working very hard to make these tools possible and implementing them successfully. Thank you.
Thank you very much, Angel. Very, very interesting talk, even for a lowly geologist like myself. I appreciated the geological input as well. Okay, if we get time, there might be opportunity for some questions at the end of this session, but we'll try and keep to time as best as we can, so I'll move straight on to the next presenter in this session, and that is Mr. Darjan Zhilikabayev, who is from AltynAlmas, and he will be talking about schedules for haulage dumping and blending simultaneously.
Добрый день.
Good day, I am Darjan Zhilikabayev. I'm the head of the unit on strategic mining planning of the company AltynAlmas. And today I want to talk about the comprehensive approach on planning, which is applied in our company. A couple of words about the company proper. We are the company AltynAlmas. We are one of the leading gold extracting companies. We have 9 deposits in 4 regions of the country. We have around 4,000 of people who work in our company. But before talking about the planning, I want to tell you why do we need it. Our company carries out different studies, develops projects from concept up to the feasibility study. To carry out this kind of work, our company developed our internal standard on the project management. In this very standard, we describe the level of development of each discipline pertaining to the project, and each project starts with the evaluation based on the standard, which we show, for instance, on this very slide. Depending on the level of development, and we carry out the studies to increase the level of this project, and our project goes through the verification at the internal level and by the external consultants, and we get verification by Kazrc and Georgia. So we, as a unit on strategic mining planning, participates in this kind of work. In order to transfer the resources to the reserve, we carry out to do certain objectives, and one of the most difficult parts of it is planning of the mining operations. And in my presentation, I want to talk about the comprehensive approach which is used to planning in our company. The comprehensive approach on planning takes into account various types of aspects, for instance, type of materials, form of blocks, equipment, the technical characteristics, productivity, goals on mining, processing, rules, sequence of work, geometrical limitations of various times, and speed, density, of location of production equipment on one pushback, and many other details which help us to get the detailed mining plan. As a result of the planning, we get at the outcome is a plan which contains a short-term plan and up to the mid-term plan. I want to say a couple of words or refer to a couple of cases which helped us to improve our mining plan. One of the examples is analysis of transportation. We have in our system built-in equipment libraries with mathematical models of all mining equipment which is used by a company, and it helps us to achieve very accurate results for calculating haulage. We carried out a comparison with the system of dispersation which we use. We calculated certain ratios or coefficients based on which we could calibrate the accuracy of our calculated plans. After this kind of work, our plan coincided with the different factors at the level of 96 and 97%. The next was optimization of procurement of the equipment. So the number of calculations, it's a very simple task for engineers, and the number of the trucks that we need. it. But for us, it was very important to understand how to use the capital repairs to increase the indicators of KTG. And when it would approach the capital repayment, sometimes will not be well justified, but we had to replace the equipment. For us, it was necessary to optimize the process of equipment purchasing, and we could do it based on such scenarios. On this very slide, in red, we show all the periods, for instance, when we had the deficiency of the equipment. In blue, we show the periods when we were planning to buy new equipment in a certain number of it, and there would be the surplus of this equipment. But in this case, or for this case, we consider various types of options, like to optimize the shoulder of haulage, they optimize the haulage and the procurement of equipment. This approach could help us to save the number of equipment and to buy or ensure a procurement in terms of time and the costs. One more case, and I want to talk about it. This is a case when we considered multi-mine analysis. Quite often we face the problems that we are lagging out overburden, which brings us to the delivery of ore to processing. But there can be cases when we cannot produce the ore with according to the required standards, and under the framework of one ore deposit, we cannot fulfill our plans. And in this case, we have to do the multi-mine analysis. When we use this very approach, we understand in which places they will be drawn down, if it's possible to solve the problem by using different other deposits, and we use different types of differentiations. The value of any long-term plan can be assessed only when we implement it. We show the analysis, for instance, of fulfillment of the plan within 1 month. In blue, we show what has not been produced. In green, we show the volumes which were scheduled and produced. In yellow, we show the blocks which were to be to be used in the future, and red, which was not scheduled at all. Why is it important to carry out this kind of analysis? Let's look at the next slide. Any lagging behind in terms of the time in the processing, we can calculate in money. For instance, the price for processing 1 ton of ore of mass totals to $5, but the plan may be 30 tons per year, but assume we have achieved only 80% of the plan, then 36 million tons are produced more, or maybe we shall produce 24 million, which is less. And even if we improve our mining plan for 1%, it will total to 822 tons of the mining mass, which is equivalent to $1.5 million per year. That is why we deal with the issues of the breakthrough planning. So based on the upper described planning, this kind of plan assumes that we should pass over from the long-term planning to the mid-term planning, and but in the mid-term plan we reflect the long-term planning. The plan is not static, and it becomes more dynamic. This is the way when we form a single or uniform plan, which can be easily changed into the strategic plan, the mid-term plan, short-term plan. In order to build a long-term plan, we use the software mapper from the and we look at the product executor for short-term planning. This system helps to implement the concept of the full breakthrough planning. On the slide, we show when from the long-term plan we can load the blocks for the nearest 2 months, which are shown in red blocks. It ensures us flexibility, ensures a possibility to follow the plan. This kind of plan means repetition of these 5 steps. Each month we'll load the updated block model. So the purposes of extraction and processing, we create the long-term plans, and from the long-term plans we make short-term plans. We create short-term plans, and automatically we create the forecast top basis for the end of the month, and in this way these short-term plans and long-term plans are ever in the actual status, and this is the approach which helps us and enables us to use this kind of planning. Thank you very much.
Okay, we're moving on to the third talk in this session now, and I'd like to introduce Britt Blumel from ALS Goldspot Discoveries. Britt has literally flown halfway around the world from her home in Vancouver, 12 hours difference for this presentation and for a series of meetings in Kazakhstan. And Britt will be talking about using machine learning and AI in improving success rates, I guess, in exploration. So I'm very much looking forward to hearing this talk. Britt? Okay.
Good afternoon, everyone. Thank you so much for having me here, conference organizers and Antony, and also a significant thank you to my co-authors who helped contribute content to the work that I'm going to share with you today. Today we'll be talking about extracting value from existing data to add confidence to exploration decisions across the mining value chain and streamline mining processes. So the presentation is divided into 2 parts. In the first part, we will together demystify artificial intelligence and machine learning. And in the second part, I'll go through a few pretty quick case studies. The first is machine-assisted geological mapping from geophysics. The second will be image analysis to predict the location and orientation of ore chutes. And the third is ore body knowledge to support mining decisions. So, I like this comic quite a bit because I feel like this nicely illustrates a problem that we see a lot when people talk about artificial intelligence and machine learning. So we have 2 gentlemen, 2 mathematicians speaking by a blackboard, and there are a lot of numeric functions and linear equations on the board, and then in step 2, a miracle occurs. And one of the mathematicians says, I think you should be more explicit in step 2. And why I think this has relevance to our work in artificial intelligence and machine learning is that often we hear people talk about it as a black box or as a silver bullet. And I'm here today to speak with you about how that is patently untrue. It is many things. It's chiefly math, but it is certainly not a mysterious black box, and it's not a silver bullet. And anyone who tries to tell you otherwise, you send them to me, okay? So we'll start with some terminology. we have artificial intelligence, machine learning, and deep learning, and all three of those fields are subfields within the field of data science. So starting with artificial intelligence, this is using data to impart human-like decision-making to machines. There's also machine learning, which is using data to make optimized inferences and predictions. This word predictions is very important, and we'll come back to this a few times through the presentation. And the third is deep learning, using complex algorithms. And so in the field of deep learning, you might be familiar with it from something like ChatGPT. Maybe a quick show of hands of anyone that has heard of or used ChatGPT. Oh yeah, everybody, great. You guys are all very familiar with deep learning. Fabulous. This is an example of a large learning model. Some other examples of deep learning that we'll talk about a bit later are neural networks, for example, convolutional neural networks, artificial neural networks. So all three of these subfields live within the field of data science, and the critical point of data science is to use data to answer a question or provide value. So you could imagine that the quality of your output or the quality of your data science work is directly proportional to the quality of your input question. The whole thing we're trying to do is have a really good, fairly scoped or focused, scoped question that we try to answer. Perfect. Last slide about machine learning, and then we'll get into the case studies. So broadly, there are two categories of machine learning. The first is supervised learning, and this is a knowledge-driven techniques. So this includes using discrimination functions based on prior observations to apply labels or classifications to new or unknown or incoming data. The second category is unsupervised learning, and unsupervised learning is about finding groupings or similarities in high dimensionality space with limited preconceptions of how those data points are arranged. So you're probably very familiar with something like clustering. You may also be familiar with dimensionality reduction, like a principal components analysis. These are all examples of unsupervised learning. So perhaps you're more familiar with machine learning than you thought. Perfect. So starting with case study number 1, we're going to do some machine-assisted geological mapping from geophysics. So this is the workflow. This is an unsupervised workflow. We're going to do some clustering, as I mentioned. Clustering is an unsupervised or data-driven technique. And in this case, we have 3 steps. We start by establishing our input features, then we do some machine learning, and finally we do some interpretation. And the take-home message from this slide is that in every step along the way, it's critical to have our geologist involved, because when we, step 1, establish input features, we're going to choose perhaps from some geophysical layers, or perhaps we'll choose some remote sensing outputs, or maybe a digital elevation model. It's up to the geologist to inform or to suggest which input features are the most relevant, going back to my geological question of interest. So it's very important to have our geologist involved here. The next step, in step 2, we'll use some unsupervised algorithms to group the data together into clusters that have similar characteristics or similar properties. And in step 3, in the interpretation, we try to relate the output from the machine learning process back to geology. And of course, our geologist is involved here. So step 1, establish input features. Here we have some magnetics data, and we're looking at some derivative products from a magnetics source. So these are our 4 derivative products, all from one particular data source, like magnetics. And our second set of input features is airborne EM data, so airborne MT. This is ZTEM or ZTEM if you're from the United States. I'm from Canada, so I call it ZTEM. And we have a few different dimensionality reduced input layers here. So we see in phase PC1, PC2, and we see PC, you can think principal component. Principal component is a type of dimensionality reduction. So this is an unsupervised method within another unsupervised method. So then we take our data stack comprised of our magnetics data plus derivative products, our EM data plus derivative products, and we cluster them together, and each pixel in this resulting map has a similar geophysical characteristic or similar signature to the other pixels that are colored in the same color. And looking at this map, I'm a geologist. This map doesn't look very good to me because the colors are super weird. That's okay. We'll compare it with our current geological map, which was maybe 1 to 250 scale done by the Geological Survey, and we see right away that our machine-assisted geological map is considerably more detailed. So we can recolor this geological map, reapproximate to our current geological map from the Geological Survey, and now we can start interpreting those clustered results, and we can see there's a lot more detail in this map. If we zoom in, anyways, we're going to zoom into a section, and we can start to compare. And one of the additional things we can do when we have this higher resolution geological map that we've derived from geophysics is we can start to actually add faults to this map, because we can see displacement on our geological units that we couldn't see before because the map was quite low resolution. So we have not only a geological interpretation, but also a structural interpretation, all coming from geophysics, assisted by the machine, but really curated by the geologist. Case study number 2. We're going to use machine vision, so deep learning, to predict the location and orientation of ore chutes in 3 dimensions. So we'll start with a tiny little crash course in image analysis. So we talked about convolutional neural networks, artificial neural networks. These are our types of deep learning algorithms. And in this case, we were using a platform called LithoLens. LithoLens was derived or sort of developed by us at Goldspot over the past several years. And it's a machine vision technology to extract numeric data, so that Excel table, to extract numeric data from a photograph of core. And it does this in a few separate, distinct steps. Step 1 is to strip away everything in that photo in the bottom left, strip away everything that's not rock. And then the next step, where there's some cleaning, some deglaring, some filtering, and then the step after that is to take your collar and your survey information, as if you were going to, thank you, to desurvey your hole in 3 dimensions, and we then have a linearized, I don't think that word is going to translate very well, a linearized core photo in 3 dimensions. And so when we have our core photo in that orientation, what we're able to do is some really neat data extraction. So what could we extract here? Maybe color. We could also extract texture from the rock. We could extract fracture frequency, rock quality, vein generation. So if the veins have a different visual characteristic, we can separate different vein types, vein area, lots of different things. The rule of thumb is if you can see it with your eye, you can train a machine to see it as well. So, same set of steps that we went through in the first example, except now we're doing some supervised work. Our first case study was unsupervised. This is supervised. So our input features here are completely different. In this case, we're going to use geochemistry from the laboratory, like ALS, and we're also going to use the image analysis numeric data that we took off of our core photography. So we'll bundle those things together, and we're going to try and make some predictions or classifications, this is supervised, so classifications, about where our ore is going to be and the likelihood of those locations. So step 2, we're establishing our target variables, our cutoff grades, and in step 3, we're going through and doing the model training and evaluation. You'll see here we've trained and tested several different models, including logistic regression, naive Bayes, support vector calculation, and random forests. We test them all and see which one is the most appropriate for this particular geological question of interest. There's lots of models to choose from. Which one really depends on your question and your data. And so finally in step 4, we get to interpret and then model these numeric shells in 3D. So what we're modeling here is the probability or the likelihood or the confidence of the presence of mineralization at that particular location. And if we look at these shells, these numeric shells, we can actually start to identify ore chutes, to not only see the location, but also the orientation of ore chutes. And this was all done just using photographs and a little bit of geochemistry. So this is very, very useful, but where I think is perhaps most useful is we can close the loop and bring this information back to the core shed, back to our geologist, because when we do some machine learning work, we actually afterwards have the ability to take the lid off and look inside and evaluate which features were the most weighty, I guess, had the most weight or were the most important or influential. And here I can see that color was very, very significant. So if you look on the left-hand side here, no, it's not going to show up. Do I have a mouse? I don't think so. Oh, okay, that's fine. So if you look on the left-hand side, at the top of those color bars, we see some individual bars, and those are the color extracted from the rock. So this is the color of the rock. And then immediately next to that, we have a strip that goes from hot to cold. So the top 5 color bars are the color of the rock that's the most important in distinguishing or identifying when we're close to mineralization. The geologist will look at those colors and say, perfect, we have a relationship with iron oxide alteration. So we can go back to our geologists and basically help them identify when they're getting close to mineralization and by which colors. So, very, very, very swiftly, we'll just talk about ore body knowledge. And I have 2 slides for ore body knowledge. The first is that you can use machine learning to do something like predict recovery. So in this example, we're putting together a copper assay with shortwave infrared data from something like CoreScan or TerraCore. We also have geochemistry from the laboratory, a couple of different ratios to proxy for rock type and alteration type. And then the bottom 3 horizontal graphs are numeric data extracted from core photos. We can bin all of these things together. This is a single drill hole from an Andean porphyry, and it's about 900 meters of depth there on the bottom. And we can predict the recovery in this mine environment with up to 90% accuracy using hyperspectral, geochemistry, and image outputs together. Last but not least, we can also do something like predict hardness. So we can infer the SiO2 content as a proxy for bulk rock mass hardness, and we can put that together with something like image analysis to identify cobbles in a conglomerate to adapt that run-of-mill and optimize recovery. So physical properties of a rock have, of course, a huge impact on the project economics. And then in summary, I'll stop there. Okay, yeah, perfect. Thank you all very much for your time.
Thank you very much, Britt, for the really, really interesting talk. There's a huge amount of information there and some great potential for the future of how technology can really help geologists in the future there. So look forward to discussing that later. Okay, we're moving on to the next talk in this session, and this will be given by Ivan Korniev, who is the Managing Director from Inderad. And Ivan will be talking about innovative radar technologies as the basis for digitalization of bulk material handling. Ivan?
Thank you. Спасибо.
Thank you. So, dear colleagues, I am the expert of the company that is working with the development of digital solutions on the basis of radar technologies. And my report will be focused mainly on transportation issues and storage issue of different loads at different stages from the very beginning up to the release of final products, and how our radar technologies could help in digitalization and in accounting of all these processes. So mainly I will be speaking about transportation and storage of bulk cargo. So I have here some historical data on different industrial revolutions, and I want to say that 3 industrial revolutions have already been successfully presented in the life of the humankind. We saw different technologies, and now we understand that digitalization brought a lot, and many experts now can say that we are living in the era of the 4th industrial revolution, and this growth is not linear one, it's exponential, and some of the philosophers and some of the physics, they quite fear of such statement. But in general, all this digitalization is aimed at one thing. So here we speak about the specific level of digitalization so that enterprises would be competitive in the market. And actually all over the world and here in Kazakhstan, we know that mining industry is quite complex industry. There is a technological chain started from the initial work and up to the release of the products. And we are all used to the fact that standard technologies, that we are all used to that we can manage at the lower level like PLC, SCADA. They are all well developed and well implemented. However, when we speak about the technologies where we have to make some strategic decisions, we understand that the value of data that we receive from the bottom level, this data is really important. So the more information we get from the bottom, the more valuable they will be at the level of making strategic decisions. And here we also speak about all these material flows. You know, the field work data, their collection is automated quite well. We are using different type of equipments, and radar technologies allows to assess productivity of this flow and transporting system. We can also assess and measure the volume of materials at different stages. We can control the remaining materials, so we can understand the volume of loading of our train stocks, and we also can see the presence of the employees at the most important things and locations. So radar technology can give us a new level of productivity, and we see here high potential. So I will skip some of my slides because I have lots of information. So why we speak about radars? Let me come to this point. Well, first of all, the value of information is based on its accuracy and reliability and access during all these operations. Well, basically 24/7. We have main problems in this industry, and we understand that we have some weather conditions like snow, dust, fog, and now we say that we want to eliminate the manual operations and we want to use automation system because it is very important also to use here machine vision, and radars could be used here because the technologies of radars have already been applied for more than 100 years, and reliability and precision is quite high. And we know that radar is usually used in air and marine navigation and all these cruise controls that we used in our everyday cars, passengers' cars. It also means something. So that's why the radar works on the specific wavelengths. If we speak about laser technologies, they have the wavelengths that is measured in micrometers. However, radars have the wavelengths in the millimeter range, and all this fine dust like fog or some kind of mud or dust. So this will not prevent radar from working well. And that's why radars are used now in digitalization in such industries as mining. And now more and more people are switching from traditional laser technology to radar technologies because they are very accurate, they are very precise. Here you can see some business cases or examples that allowed the facilities to improve their indicators, to improve transportation parameters. For example, here we see the rotor escalator at the iron ore facility in Australia. So we use their radars, and we see the 110% increase in ore shipments, and we see the reduction by 75% in peak loads for the drive.
На руднике в Чили за счет онлайн-мониторинга в условиях сильнейшего опыления при разгрузке самосвалов в приемную емкость дробилки радары позволили автоматизировать подачу самосвалов без участия оператора, поскольку контроль визуальный уже не был необходим. И это позволило на 25% увеличить рост разгрузок в час и на 13% снизить простой машин в очередях на разгрузку. И еще один интересный пример – это цифровой двойник вагона погрузки руды в Австралии, позволил на 28% снизить время погрузки на состав и на 2% больше грузить на вагон. Это как одни из таких ярких примеров. Теперь несколько слайдов, посвященных другим вопросам применения радаров. Они могут применяться как на локальных системах, так и в системах работающих на связи между технологическими переделами. Извечный спор рудник-фабрика, кто сколько отгрузил, он никуда не делся до сих пор, и с применением радаров можно некий арбитраж проводить на стыке этих переделов, так и на стыке фабрики с более высоким переделом при отгрузке концентратов. Ну и несколько примеров еще. Вот цифровой двойник роботизированной откатки и дробления, построенный на различных радарных технологиях. Несколько примеров цифровых двойников складских помещений и складов открытого типа. Шихтовальные дворы, усреднительные склады, которые оперируют с крупнотоннажным погрузочно-разгрузочным оборудованием, также в настоящее время с помощью радарной техники подлежат цифровизации, и данные, получаемые в эти системы, и аналитика, которая в дальнейшем строится на них, они весьма точны. И это находит все больше и большее применение. Также к цифровым двойникам материала на складах можно добавлять информацию, например, с поточных анализаторов или лабораторные данные, и накапливать информацию о свойствах материала в объеме. В конечном итоге получая, например, модель распределения качества материала в штабеле и оптимизировав таким образом усреднение и отгрузку по спецификации. Всевозможные силосы, бункеры, рудоспуски различной протяженностью с помощью радарной техники в условиях самого жесткого пыления позволяют получать точную информацию по остаткам в режиме онлайн. Ну, как я уже говорил, системы автоматизации крупнотоннажного погрузочно-разгрузочного оборудования, построенные с применением радарных технологий, работают на порядок эффективнее с минимальными простоями. Просто из-за того, что сенсоры всегда работают в сложных пылевых условиях, не нужно дополнительное время на остановку и обслуживание именно систем автоматизации. То же самое касается штабелирования, вагона погрузки, о которой я говорил. И в заключение слайд, посвященный системам безопасности, в частности на радарных технологиях, строятся в настоящее время самые современные системы противодействия столкновениям подвижного состава как при подземной добыче, так и на открытых площадках. При этом радарные технологии здесь позволяют полностью избавиться от проблем конвенциональных сенсоров, которые раньше применялись, и работать в самых сложных условиях по пыли, снегу, влаге и туману. Ну и в заключение слайд, который посвящен высказыванию Клауса Шваба. Он написал интересную книжку, посвященную проблемам, даже уже 2 книжки он выпустил, посвященные проблемам 4-й технической революции, рекомендую их прочитать. Но важно то, что четвертая революция промышленная будет такой же мощной и влиятельной, как и все три предыдущие вместе. Ну и мы уже, на мой взгляд, начинаем потихоньку это ощущать. Спасибо за внимание.
Thank you very much, Ivan. Very, very interesting talk. Thank you. Okay, moving on to the next talk in the session, I'd like to invite Nikolai Konovalov, who's from Scania Mining in Sweden, and he will be talking about a lean mindset for cost-effective, sustainable mining transportation. Over to you.
Здравствуйте, коллеги. Я решил сделать презентацию таким образом, что слайды у меня будут на английском языке, а говорить я буду на русском. Вот, чтобы всем...
Arranged my presentation, so I arranged my presentation in the English, but I'll speak the Russian. My presentation is lean mindset for cost effectiveness, sustainable mining transportation. Is called like that. Why? Careful production. On the first slide, I shall show to you, and you will see a conveyor, Scania, Scania. On the conveyor, they use the PSPS system, Scania production system, which is based on two major principles. The first is it's a module production system, which means that we have a set of standard components with standard interfaces, which can be used as boxes of Lego and put in different combinations, where you can get this or that unit of the vehicle, segments of buses, and whatever you like. The second principle of Scania, of ASPS, the so-called lean principle, a lean way of working, as we call it in the Russian language. Efficiency of using these two principles is displayed on the stand. Figures speak for themselves. For 22 years, we were able to increase the specific production twice per each employee. In 1995, we produced 3.5 vehicles, but in 2017, 7. But now this figure is higher. What is behind this principle of line production? There are several instruments which we can name: balanced flow, cycle time, takt time, visualization, eliminate waste, eliminate waste which are not desirable, and continuous improvement. Why? I want to draw your attention to this, because if you look attentively, or after we have looked attentively, we came that transportation in mining and conveyor Scania, there are so many similarities. We have the place for transportation, unloading, handling. Transport units will go back to the place of loading and unloading. It's a loop type of a conveyor. And when we apply this very lean way of working, we ask the question, what is your process, the process of your transportation or haulage? And the second is, how do you know that it works, that it should work? And the third, if not, then how you can improve this? In order to improve something, we all understand that we need to understand the current situation. That is why we do mapping and monitoring of the current situation about how does the transport situation happens now. How do we do it? In fact, it's done in a simple way. We have a set which is called a site mapping kit. We use the action camera, a second meter for registration of the takt or cycle time, and also assessment of the loading factors time and transportation time. We'll talk about it later. And when we talk about time, what kind of inefficiencies we can see? Idle, huge queues of cars waiting for being loaded. If we talk about the factor of loading, it's overloading, which bring to the undesirable consequences, or maybe unmatched equipment, unmatching equipment. The roads, problem with the roads, but the roads are not in a good condition. For instance, they should be in good condition, otherwise we can have some technical problems like elements of transmission and etc. Failures in transport means. Now we'll talk about the takt and cycle time, how to use it to measure productivity. Let me remind you that the takt time and cycle time are used in the production process of Scania. The takt time, cycle time, what is it? Takt time is the time how often a loading equipment sends away a loaded truck, and it measures the productivity of loading equipment. A cycle time is the time is taken for a truck to complete a cycle. Loading, unloading, coming back to the place of loading. The takt time and cycle time should be fitting each other ideally. And we go back again to balancing the flow. We go back to production of Scania. How can we achieve balancing of the flow? It's quite simple. In different mining enterprises worldwide, we can see examples when this principle is sometimes not followed. The number of the equipment is defined by by arithmetics, dividing the time of the takt time to cycle time, and you see a chain here. We see that we don't have enough of trucks. That's why the excavator is idling. 6 trucks produce 515 tons per hour. The time of takt is something, and we know that excavator idling is very, very undesirable. Excavator is waiting 4 minutes, 40 seconds of takt time and 28 minutes cycle, which is not good because the trucks are waiting for being loaded. Yes, of course, we transport 600 tons per hour, but the time of takt is reduced because the excavator is loading, but the time of cycle will increase for 36 minutes. In this very case, in this slide, third slide demonstrates a well-balanced flow, and it's like in a conveyor. When the excavator loads the truck, the next one will come. The time of takt is 4 minutes, cycle 28 minutes, and 7 trucks already produce 600 tons per hour without any losses. And this instrument, which I show, is called site mapping. On this slide, on that slide, we show what I have already talked about. We have the instrument which is called the total calculating economy. We can simulate productivity and the costs incurring of the transport, providing the parameters which can be of great interest to us. It's the cost of the ton of transported load. What do we have? I think that you all know that trucks of Scania are reliable, saving, but we have different types of trucks for different kinds of works, for inter-quarry transportation, haulage of materials for outbound, long haul, integrated hauling, underground hauling, support and service vehicles, transport, or for transportation of personnel, buses for transportation of the personnel. And generally, we understand that the quarry conditions are very difficult at remote distances. That's why we ensure maintenance of the equipment by spare parts available, or we can, the client can provide such spare parts, and there is a mechanic in place who can ensure the readiness of the equipment. A couple of slides. It's in pit haulage truck. It's a truck. Self-dumping. It's like a road motor car, no, but it's not. It has strong transmission, bridges. It's a really quarry truck. There are different versions of 4 axles, and it's so in and outbound haulage from the quarry. And if it was about the following. We all talk about sustainability, about sustainable development. Scania is not standing aside from it. We have for it different solutions. On this slide, I want to show to you use of the diesel equipment. Well, now we're talking about the electromobiles, but when we use the diesel consuming transportation means in Scania, for instance, consumption of fuel is 2.3 times lower versus the same analogous vehicles who transport the same material. We decrease 3 times emissions to the environment, and we show you its schematical footprint. And the next is about this steps to be undertaken. It's electrification of the transport. So these are really working transport means we work in Norway, Australia, and Sweden. Photos speak for themselves. I wanted to show a small video to you, but there is not much time left. This is a really working truck in Sweden, which transports the mass of ore. So we, in production of our trucks, we help our clients to use these trucks in real life. For it, we have the solutions, products, instruments, and you can see here how we show the law of the evolution. Future belongs to those who are smarter. And this is the Archaeological Museum. Thank you for your attention. We have a stand by. There are booklets. You can come up to me, ask your questions if you are interested. Thank you.
Thank you, Nicola. Very interesting talk, and I like the video at the end as well. Nothing excites me more than lots of big trucks. Okay, so we're in the final talk of this session now. And last but not least, I'd like to introduce Artur Akhmetov from CMT Consulting, who will be talking about different ways of assessing capital and operating costs of mining enterprises. Artur?
Hello, ladies and gentlemen. Здравствуйте, уважаемые дамы и господа.
Hello, ladies and gentlemen. My presentation will be in Russian language, and I will be. My presentation is in Russian. I will be speaking Russian, and I'm pretty sure that it will be the simultaneous interpretation provided to other people. So today we are going to speak about selection and justification of analogs for estimation in capital and operating costs of a mining enterprise. This topic is very relevant because we shall do the pre-project study at the greenfield level, and the company at the early stage shall to have the rationalized structure of operational OPEX and CAPEX, so that to provide for the forecast. So we know that there are different tendencies in mining industries, and sometimes we see some uplifting and downlifting situations. So we've heard about these cycles, different cycles before from our colleagues, and they I think that people here understand this topic, and despite the fact that there are some studies, when people are using consulting company service, they have some higher requirements to the precision. So my presentation will show the methodology, and this methodology is used by our company when we do study the project at the preliminary feasibility study. We have a multiple factor approach, and this methodology will help mining specialists to take the reasoned decision at the early stage of the product and to increase the quality of the study. So this slide presents the project life cycle stages, and we see that at each stages there are different goals and there are different specificities. I'm not going to speak in all details about each of these stages, but I am pretty sure that you know all this information. Well, I just briefly mentioned some of the ideas. At the initial stage of the exploration, we need to have the conceptual study of the project so that to have reasons for investment. And then after, we have some preliminary feasibility studies that would show the increasing level of technical and economic knowledge that have been received at the earlier stages. Here we look at the different scales of the project, its configuration, the technologies that would be applied, plan, location. Then the program has been prepared for the further geological works, and then the rationale for further study. Then these studies would come to final technical and economic assessment that would speak about the feasibility of the project with a specific confidence level that would allow to make a decision about this deposit. So we need to see the good ratio of risks and benefits based on the result of the analysis. And at the following stages, the company would come to the implementation of the project, the construction, the commissioning, and then operation. So we need to understand the direct costs, we need to understand the equipment that will be used, the consumables, the materials, the calculation of the personnel, the use of the services of the contractors, and also knowledge on different production processes. And then if we move by the stages, we need to have a higher assessment, higher precision assessment, and when we choose different projects, of course, the most potential project at the initial state, when we do the final stage, it might not be recognized as beneficial. So right now, tendency is mainly the following one: we would choose the best and the optimal project for the future. So we have to specify the specific range for technical and economic technical feasibility study from 10 to 15%. This is the level of accuracy. And if we speak about standard equipment that will be used. So speaking about this methodology, we use different ways. So we use the cost estimation methods, where the performance of one project is obtained by extrapolating and interpolating the performance of another project, so according to scale, resource size, and other characteristics. And when we study enterprise at the stage of preliminary feasibility study, we cannot do it without some specific characteristics. So we need to have the basic information, we need to have the geological conditions, mineral resources data, topography, climate data, electric supply, water supply, access to these sites, and some other data. And quite often we need to use some specific indices. For example, we use the consumer price index. This means that the focus should be shifted towards individual input evaluation. For example, the price for steel, concrete, copper, for energy. When we use the objects, analog objects, we are using the following principles. So the costs shall be actual or shall be based at some technical and feasibility proposal. We need to increase the accuracy of the cost estimation, and also we need to think about some other specific characteristics like geological. And it is important so that our analog object would have the same type of raw materials, the same scale, and some other factors. And as a rule, at the stage of preliminary feasibility study, we have the several stages of the development of deposit, and we might have different types of processes, different types of the price of the final products. And now, so that to have objective comparison of different options between each other, we do the breakdown of capital and operational expenses, and we create different options that will take into account some specific assumptions. So we also have different potential for the development of deposits. And also we need to do the climatic characteristic study. We also have some specific characteristics, and we assess the territorial development of the area. If we speak about application of some currency coefficient, we also have several approaches here, and as a rule, our company has the well-established practice. So taking into account territorial location of this asset, we also use reliable source, dated source, so that to use the specific inflation parameters and the price for the fossil fuel. So we need to use the industrial analytics, the data from the Ministry of Economy, the data from the central bank. As for the coefficient of the work volume, we also use different methodologies. So we use the mean. So we have the rule of 60s, where we assess productivity and can calculate the cost. So usually we compare, for example, one enterprise with the future enterprise with the existing enterprise if they have similar characteristics. We also use the method of the other evaluation. So when we do the construction and installation work, so when we construct a specific object or when we speak about delivery of specific equipment, we take into account the coefficient for delivery and installation. And when we do the preliminary feasibility study, the coefficient for installation would be 5–10% from the initial cost. So here you can see the example, and here we are using different coefficient indexes. So, for example, here we are speaking about the main ventilation installation. We calculated the amount of air for ventilation, and we chose the similar ventilation installation that would meet the requirements. And we knew the price of the equipment. And we saw that analog object had the price for the year 2019, and then we did the specific coefficient work. So we applied the specific methodology. So indexes that are formed by the Ministry of Construction of Russian Federation, and these indices are publicly available. As for the other CIS countries, these indices also could be used. But we need to make sure that they have similar parameters. And in the international practice, we also have different international standards and indices. For example, the Australian reference, statistical reference, and some other examples and guidance. Also, we use the specific index that would take into account the increase in the price. And we see that here our equipment would be 25% higher than the one that we did comparison with. So when we are speaking about some other installations, for example, construction of horizontal or vertical lines or conveyor belts, we need to take into account, of course, the volume of work and the productivity of this deposit. And as our facility was in the CS country, we used also the currency coefficient. So we are using the analog facility so that to make the estimation for the cost of the facilities that we are working. So finally, I would like to say that nowadays the company pays lots of attention to the accuracy of cost estimation at the initial part of the project, despite the limitations of the basic data. The proposed methodology for cost estimation allows us to minimize risks and allows us to optimize the options, and we can make a decision from the economic point of view. When we prepare the cost estimation, we need to use integrated approach that is based on multi-factor analysis, and the approach of our company is based on the using of specific database based on our experience that we have accumulated working in the mining industry. Our database allows us to do the right calculations, and later these databases and data are used in our project. We need to use the specific approach in choosing the analog objects, and then we can make sure that our estimation is accurate and precise. Thank you so much.
Thank you, Anton, for concluding this section. Before we conclude everything, I'd just like to ask everyone in the audience to show your appreciation once more for all of the speakers in this session by congratulating them for some excellent talks. So thank you very much to everyone. Okay, we've actually done very well on the timekeeping in this session, so there is a couple of minutes free before we break for coffee. So perhaps maybe I could ask the organisers if you could put up the QR codes again to give more people more time to respond to the survey that Artur has asked us to put together. So the one on the QR code on the left is for the responses in English, and the one on the right is for Russian. So if you want to respond, now is your opportunity to do so. And then I know the organisers will be very grateful for any responses that you want to put. I'll just give you a couple of minutes. So while people are busy entering any final responses in the questionnaire, I'd like to thank everybody here again for attending this session. I know it's quite late in the day now and it's quite warm in here, but I hope you'll agree it's been an excellent session. And I think it's almost time for a well-deserved coffee break. So thank you again. Do you want me to put the responses up? Fine, I'll leave it for now then, okay. But if I can leave you to conclude your responses in that, I'm sure the organisers will be very grateful to see your responses to the questionnaire. So thank you again for attending this session, and I will leave you now. And yeah, I think we're all entitled to a well-deserved break and a coffee upstairs before the next session. So thank you again.